Hi everyone! In this video, we're going to be talking about lines and planes in three-dimensional space. And so first thing I want to introduce to you is this notation right here. So this R, fancy script R to the third power tells us we're in a three-dimensional space of real numbers. And then we have been working with previously two-dimensional space, which is that same script R to the second power. Now let's first recall some of the stuff that we know about two-dimensional space. So one thing is we are very familiar with working in the XY plane. And so we have our two axes, the X and the Y axis, and we have worked with lines in that space as well. So let me just draw a random line here. And normally, we like to use the slope-intercept form, so y equals mx plus b. We know b is the y-intercept and m is the slope. And remember, m, that is our change in x, or our change in y divided by our change in x. And so if we think of this slope as being, as we have here, m equals b over a, where a is the change in x and b is the change in y, we can think of this as a directional vector and write this as a comma b. And so we can also represent this is component form, but we also have standard form of v equals a times the unit vector I plus b times the unit vector j. And now that we know this different way of thinking about our slope and using vectors to express that, what about three-dimensional lines? And so now we no longer just have our x and our y coordinate plane, we have the x, y, z space. And so now we're working with ordered triples like this one here. And so now our directional vector is also going to have to be three dimensions, have an x, a y, and a z component. And that's shown here in this vector v. So I is the direction of x, j is in the direction of y, and k is in the direction of z. And so we're going to be working with the parametric forms of lines in three dimensions. And so here we have a formal definition. And so if you'll recall, we have worked with parametric forms of lines in two dimensions, which are very similar to this, but now we have the third dimension, so we need a third equation for z. So one thing I want to point out here is that these knots, so the x naught, y naught, and z naught, that is a point, so we'll get that from an ordered triple that is on the line that we're looking for. And then we also will be given a directional vector, so this vector v here, and that is going to tell us the direction of the line that we are creating with these equations. And you'll notice that the coefficients of t are from that directional vector. So a is for x, b is going to be in the y equation, and c with the z equation. The symmetric equations is actually the very same thing as these parametric forms. The only difference is that in order to set them all equal like this, we divide each equation by the coefficient of t. So we're dividing the x equation by a on both sides. The y equation is by b on both sides. And the z equation we're dividing by c. And then we can set all those expressions equal because we will have gotten those expressions all equal t. One thing I also want to point out is that our directional vector, a, b, and c, that is actually a parallel line. And so here, if I was given a, b, c, and then in our problems, we'll also be given a point. So what we're really doing here is we're finding this line that contains that given point and is parallel to our given vector. All right, And we'll see an example of this in just a second. But now we need to answer, what is a plane in 3 dimensions? And so, like I said, we have been working a lot in the XY plane since probably middle school for many of you. And now we're considering this 3-dimensional space that's actually going to be having 3 coordinate planes in it. And so when we have that, we're looking at these types of equations. So we have a point normal form equation and a standard form equation. They're actually very similar to each other. The standard form is actually just a simplification of the point normal form. And so with these 2-dimensional surfaces that we call planes, we are going to be given a point, x naught, y naught, z naught, and then also a vector, very similar to the case of our lines. But in this case, our vector that we're given, which we'll call n, is actually a normal vector. And so what that means is it's going to be perpendicular to the plane that we are constructing with these equations. So why are we worried about lines and planes in 3-dimensional space? Why is this important? Well, in Calc 3, it is all about multivariable calculus. So we're working with more variables than we have before. We're having this x, y, and z, this 3-dimensional space. And so in order to understand the types of shapes that we're going to be working with later on in the course, we need to start with lines and planes because these are the building blocks of those shapes that we will see later on. And so if you think about it, think about the room that you're in right now, or if you want to, look at this picture as well. And so you can think about in that room, it's made up of planes or the walls. And if you see in the corner of the room, we have a line at where those planes intersect. Same thing at where the walls meet the floor, we get a line of intersection, and where the walls meet the ceiling. And if we think about it, a line is a one-dimensional thing that contains infinitely many points, but the planes are 2-dimensional things that contain infinitely many lines. And so it's important to understand the definition of a line specific to 3 dimensions. Because like I said, in 2 dimensions, you're only considering x and y, but we also have that third variable of z, what's going on there. That's what we need to understand. So let's go ahead and first look at writing parametric equations for a line that contains the point 1, 2, 3, and is aligned with a vector v, 2i plus j minus k. And then we're also asked to find where this line passes through the coordinate planes. Very first thing is using that parametric form definition. So if we go back, we see that we need to find the x naught, y naught, and z naught, and then also identify the a, b, and c. And so if we look, we have our point given to us. So this is going to be our x naught is 1, our y naught is 2, and our z naught is going to be 3. And then we're also given that directional vector, which has our coefficients. A is going to be 2, because that's the coefficient of I. Our b is going to be 1. Remember, there is no coefficient of j, so it's going to be a 1. And then our c is going to be a -1. Be careful and make sure you include the signs. So since that's a negative k, it's going to be a -1 for our c. So now we apply that to or plug those into our equations. So let me just rewrite our parametric form. And then we will plug in. So our x naught we had was 1. And our a we have is 2. Our y naught was 2. And our b is a +1. And then our z naught is 3. And c is -1. And then we can go ahead and also solve for our x, y, and z. So we're going to add these numbers to both sides of our equations. So for x minus 1 equals 2t, we're going to get x equals 2t plus 1. We get y equals t plus 2. And then z, we get negative t plus 3. So this is our parametric equations for our line that contains 1, 2, 3, and is aligned with our vector v here. Now, don't forget this second part. We're asked to find where this line passes through the coordinate planes. And so if you think of our three-dimensional space, let me try and draw that here. We have three axes, which this is not drawn very well. But we have our x, our y, and our z. So we have three different planes that we can consider here for our coordinate planes. We have the xy plane that we've worked with the most. We have our yz plane and our xz plane. So we would need to find where our line that we just created intersects these three planes. So let's consider the xy plane. So first thing is you'll notice that in the xy plane, we don't have a z in the title of this plane. And so therefore, that means that our z, it's not that we don't have one, it's that it's 0. So we've set it equal to 0 in order to strictly work with the xy plane. And so now in our original equations that we've come up with for our line, we're going to plug in 0 for z, and we're going to solve for t. So we get 0 equals negative t plus 3. Solving for t, I'm going to add t over, so we get t equals 3. So now we can find the values of x and y. So if we plug in 3 for t, we get x equals 2 times 3 plus 1. 2 times 3 is 6, plus 1, 7. And then for y, if we plug in 3 for t, we get 3 plus 2, which is 5. So now you'll notice that our line intersects our coordinate plane xy at a point, which makes sense because we have a one-dimensional thing, a line, and a two-dimensional thing of a plane. So it's going to intersect at one point. And so here we have the point is this ordered triple 7, 5 for y, and then 0 for z. And then you can do the same thing for the yz plane and the xz plane. So for the yz plane, we're going to set x equal to 0. And then for the xz plane, here we set y equals to 0. And then you can always check on the solution page. I have put the points of intersection for those two planes as well with our line. All right, let's now look at, here we're given the parametric equations of a line, and we're asked to find the vector v that's in the same direction of this line. And so remember, in order to find that, if you think back to our parametric definition here, that's going to be the coefficients of our t in each of our equations. So if we look here for x, we have a negative 2t. So we're going to take the negative 2 for our a. We have a positive t in our y equation, so that's a positive 1. And then for our z, we have z equals 3t. So our coefficient 3 is c. And so here we have found our vector in the same direction as that line. All right, now for the last thing that we're going to do with our lines and planes is we are going to look at, if we're given these equations of a plane, how do we find normal vectors to the plane? And so to do this, we're going to look back at the definition of our planes. And so if we look, remember that our normal plane or normal vector is going to be this n, which is the vector ABC. So looking at our standard form of a plane, we have that A, B, and C are going to be the coefficients of our x, y, and z respectively. And so now going back to these, our first plane is given by the equation negative x plus 4y equals 3. So we have that n is going to be equal to, well, our a is the coefficient of our x, which is a negative 1 here. Our b is our coefficient of y, which is a positive 4. And our c should be our coefficient of z, which we don't have a z term, so therefore it's 0. And then we do the same thing for number 2. So here we have 0.6 x plus y minus 2 3/10 z equals 10. So our a is 6/10, our b is 1, and our c is negative 2 3/10. And then for our last plane, we have a similar situation to plane number 1, where we are missing one of our terms, and we're missing the x term. So therefore, 0 is going to be the A, 3 is B, and negative 2 is C. I hope you find this video helpful and wish you luck as you are working with lines and planes in a 3-dimensional space and continue to work in 3 dimensions in Calc 3.